It's about an hour.
An hour and a half.
1 hour and a half. 1 hour and a quarter. How is UNS
Are you making the progress?
Yes, yes, yes.
Thank you.
Yeah, yeah.
Sorry, I did it before, but somehow I
No,
don't
that's
know, like,
fine.
I was kicked out and this kicked out bubble too, but now should be fine. Well,
Okay, Slava, I think we can start now.
yeah.
Mm.
And I can also take it up and go up.
Okay, so I think thanks for everyone and thanks for your comment, everyone. So we have the last lecture from Slava, and this lecture Slava is going to talk about the um, work example effects and also how to sequence work example and problem solving for teaching and learning.
Okay, so thank you again for coming. So, everything is okay with
Not really. So there's like what is shared is actually the browser window of MS Teams with like I don't know my photo and like avatar of other participants rather than slides. So. Yeah, so this is what we did before. Okay, good now. Well, not yet. Now here you have the calendar. Now,
Okay, is that all right?
now it's good consistently everywhere.
Thank you. Okay, so today is last fifth lecture in this part of lectures, of series of lectures. And what's going to be in the second part, I will talk about in the end. Today we're talking about the topic is building knowledge base in long-term memory. Essentially, we started talking about that last time, but today we will focus specifically on explicit instruction as a means of that building knowledge in long-term memory, and explicit instructions most effectively implemented by worked examples. So we talk about worked example effect. We will talk about some sequences of explicit instruction in problem solving and the role of problem solving. And in relation to that, and again, we started a little bit about that last time, about a role of specific instructional goals as actually determinant of optimal instructional means. So again, some remind you from an evolutionary perspective. Again, we follow this sequence. Again, last time I already talked about it, just quickly list. So we talk about that information store principle, or in terms of human cognitive architecture, it's about long-term memory characteristics and so on. We talk about this principle and in association with that with characteristic of working memory in some cognitive load theory techniques for managing working memory or cognitive load in relations to this. So we talk about this principle, which applies when this natural information processing system, including human cognitive architecture, operates in some familiar environment. In terms of human architecture, it means that we're talking about some expert performance in this case, and we talk about expertise. So first three lectures. Last time we started talking about last two principles, which actually describe how the knowledge is acquired into that information store. First three principles essentially about information store and how it operates. And last two is how the knowledge is acquired. And one of those means for acquisition of knowledge into long-term memory, or generally in natural information processing system into information store, acquisition of that information pattern in a store is random generation and testing. So in terms of human cognitive architecture, it would be problem solving by problem search. So like some of the examples that we discussed last time, trial and error, mean sense analysis, those type of means that allow to essentially discover the knowledge, which is not build the knowledge, new knowledge in long-term memory. So problem solving, and we talk not only about problem solving as one of these means of acquiring knowledge, but we also talk about other role problem solving when the knowledge is available, how that essentially expert problem solving, we talk about that, and also about problem solving, about how to problem solving as a learning or instructional means. We'll look about some of those aspects, which pretty much be, tell us that they might not be really good instructional means by itself, problem solving exercises without preliminary sort of instruction into problem solving strategies or problem solving method, because that could impose very heavy cognitive load by itself. Those mean sense analysis, trial and error, and other those random or problem search techniques when people use when they don't have specific schemas to rely on. But those method and instructional means, they are always associated with high working memory load because you have to keep your goal in mind, final goal, sort of intermediate sort of sub goals, initial state, and compare all of them and figure out where you are and how to reduce that distance. And all that consumes a lot of working memory capacity and impose cognitive load. Therefore, no capacity left actually for trying to figure out to extract that schema from that experience. So therefore, we actually come up with that conclusion that it's not a good idea. Some alternative ideas were suggested, like eliminating that goal. So using goal-free problems or unspecific goal task, where the goal is eliminated and the task is reformulated, like find whatever you can in this situation, not that specific parameter or whatever. And in some situations, those goal-free problems actually working that technique, but it's quite limited use they have because they're only applicable when we're dealing with rather limited problem space, so not too many those possible solution moves available. So they all could be trace or retrace, or the students, learners could actually come and go through some of those possible, all possible problem states and associated solution moves. So could be useful, but not always. What it could be used more frequently is the worked example. So today, therefore, we will talk a little bit more about worked example or explicit instruction in general as a means of acquisition of knowledge in long-term memory. But that is related to the final, this fifth principle of natural information processing system, which is a borrowing and reorganizing principle, which actually states that most of the information in that information store or in human architecture is long-term memory is actually not rediscovered by those problem search, but actually borrowed from other stores, meaning from other people, from some, in case of human, that could be some printed material, some spoken material, some we listen to other people, we read instruction, we imitate other people, what they do, we observe, and so on. There's a lot of ways to borrow, but we're not only just borrowing, copying, therefore it's called borrowing and reorganizing, meaning that it's always transformed, reorganized. It's never actually copied literally. That's one of the mistakes that sometimes people who talk about information processing in humans, they think that information processing is sort of approach says that we just copy information. We never copy, absolutely never, zero copy. It's always reorganized in relation to what is already in knowledge base. Because without that, it's no copying possible. Because we have to copying actually maybe it's only possible when we're talking about rote learning. In this case, that could be some just copying without understanding. If we talk about learning something with any kind of understanding, that means that we reorganize. Because understanding actually means that we activate some already available schemas or some knowledge, whether it's correct or incorrect, and we actually try to understand materials as external information coming in terms of these available schemas. We just assimilate into them, right? So, and that what means that we comprehend something or understand something. Without that, so reorganizing always there. So in case of biological natural information processing system, it's that means that they actually borrow the genetic information. Well, it's some different kind of those reproduction, so that means sexual, asexual, whatever in terms of biology, because always with this comparing this human architecture with some biological systems, that they have similar principles, and that principle applies as well. But we're not going to talk about that more. But in terms of human cognition, it means that we borrow that knowledge in long-term memory from other sources and reconstruct it by integrating with already available knowledge. In terms of this integration with already available knowledge, I say that it's always there for any learning with any kind of comprehension. But you might say, but what there is no knowledge there. But again, and I already sort of answered this previously to some extent, there is always something there. At least there is some biologically primary knowledge is available in long-term memory. We can say always there is no any zero availability of any knowledge there. There is at least biological primary knowledge, and when that knowledge made explicit and reflected upon, that knowledge could be integrated with new incoming knowledge, and that could result in some sometimes misconceptions. Again, I mentioned this kind of processes, this phenomena before, but again, when completely novice learners, when any knowledge in a task area have to learn something, and the only thing that they have these biological primary intuitions that they have from living in the environment, they would integrate that incoming knowledge with those primary intuitions, those primary knowledge, what we call and we discussed in the first lecture and sometimes in the following up, and then sometimes result in some misunderstanding in terms of what we want them to know. That's result in something different. So that what is called those misconceptions, like in physics, for example, from living in everyday environment, we kind of have some people have an intuition that turning on a light in a room just brightens the dark area without the object. And scientific explanation from physical point of view, from physics, is that the light actually is something that is reflected from the objects and getting into our eyes. So it's completely different things. But intuitively, we have this kind of idea that it's just some brightening of area. And that is actually a misconception, of course, because it's just coming from that intuition that we have from living in everyday kind of environment. The similar ones, those calls like misconception or naive or intuitive conception and so on, different terms, but actually it's misconceptions. So that primary knowledge could play this negative role in many cases when we do this borrowing and reorganizing in cases where some only this primary knowledge available in long-term memory. So, and therefore some research shows that it's those misconceptions not easy to overcome. Some people can graduate from physics degree in university and still have a lot of those kind of misconceptions when they encounter this kind of phenomenon and try to explain in everyday life and other situations. So they should be challenged directly, not just some correct information presented and regarded as very sufficient. So there is a lot of literature on misconceptions, especially in science, in physics, and how to deal with them and so on. I mentioned before some of those misconceptions of children on the roundness of Earth. So again, because they come to the lesson or to the school, whenever they learn this, with this intuition that the Earth is flat, that's their everyday environment, and then they are being explained that it is round, and they therefore that integration, reorganizing, borrowing and reorganizing actually result in some bizarre sort of representations like this. So they try to integrate it in their available knowledge, the primary knowledge in this case. They try to assimilate this new information into that available knowledge in long-term memory, doing this kind of reorganizing in this way. So actually the gradual transition could be represented like this. So the initially this on the bottom is the intuition, that primary knowledge, that the flat Earth, and that gradually with experience they are coming out with some kind of those intermediate integrated form, which are misconception essentially, but finally coming up with this idea on the top is the correct. So it's all this transformation could be shown in this kind of diagram from bottom to the top, how it's happening. And it's not simple process. Take some steps of overcoming this misconception and transforming into correct scientific. So it's just to mention a little bit about this reorganizing, borrowing and reorganizing in the case when we have to reorganize it with primary knowledge available in long-term memory only. Otherwise, we will get to worked example again. So worked example as a means of that borrowing. So worked example is essentially worked example effect in cognitive load theory. So worked example, it's not something that cognitive load theory discovered. It's something that the worked examples were around for centuries, if you like. So it's, but what that this theory of cognitive architecture and cognitive load theory, what it added, that explain actually why they are effective. So why they are more effective than other instructional meals, like conventional problem solving. So, and they demonstrated, they provided a lot of empirical evidence into this. But briefly, just to define, and most of you obviously know what it is. So the work example, normally they present after the problem statement, all these kind of solution steps according to the sort of correct sort of procedure, how to do that with some explanations if necessary, up to the final sort of answer. So they provide essentially this expert-like problem solving, like step by step. Not exactly expert, because experts skip many steps because they have some automated and things, but they should in this case reverse engineer it and decompose and express it into some of those step by step how they were originally before they were automated. So expert-like step by step solution to the problem. Also, example is frequently used not in single form examples only, because if you present just many examples, the students could become possibly bored. So example problems pairs are used. So you present example and then follow for some problem to solve, similar to the situations that were described in an example. Then and again example and some problem to solve. So that regarded as a little bit something could be more motivating for students than just mixing example with problems. frequently that those example problem pairs are suggested to be used rather than example alone. So examples used not only in technical areas, I mean technical like in mathematics or science or some quantitative kind of technical discipline, but also in some of more or less hard kind of sciences, like even in literature, in other areas of, of learning. We will look at some example shortly. This is just possible example in algebra, for example. You can add some explanation possibly if students need it, but it could be self-explanatory. So you just show step by step what's happening, how to get from initial state to the final answer in the end by representing all these kind of steps gradually. This is an example from essay writing. So some example or essay is presented, and then some detailed comment what this essay actually is, consist of. So some recommendation, some guidance here. So that could be regarded as a form of worked example in this area of essay writing. Another form of a worked example in this area, like essay writing in literature studies, would be, and we experimented with one of our PhD student from Korea. Some, for example, selecting on a, if the students learning to write essay, for example, on specific topic, you present the topic and give them, let's say, 3 well-written essays. They're different, not repeating each other, of course, because essay could be written in indefinite number of different variations, right? So, but if you select just, let's say, 3, why 3? Just 3 because it's reasonable in time. Could be 5, but it takes a lot of time. But 3 is reasonable to study. You present 3 well-written essays from point of view of instructor, and that would be regarded as a worked example on essay writing. There's another form of essay. Or you can give us some general suggestions, a recommendation like in this one. So different form, but all those could be regarded as a sort of worked example in this area, non-technical area. So worked example effect in cognitive load theory, that's some kind of effect that show that starting instruction with worked examples would be more efficient than doing just conventional problem solving and hoping the students, just by solving many problems, will come out with learning of solution schema. So that was essentially what worked example effect, where they compared in controlled experimental condition groups who actually did this example or example problem pairs with a group who did only problem solving for equivalent amount of time, equivalent amount of general problems involved, as equivalent condition, just those 2 different instructional means, and they come out with this worked example effect that example conditions was significantly better. Some of those simple linear algebra equations like that were used in that study, which is pretty much this one is quoted here, is the first study in the worked example in cognitive load theory. So when students learn from worked example, they essentially attend at each time just to specific problem state, which is represented by the dotted line in that solution procedure, written procedure, and the associated move. So they see the problem state and what the move should be taken in this state. So that's exactly what is regarded as necessary for schema acquisition, because schema, that's some knowledge structures that allow you to categorize the problem, that allow you to come up in any kind of problem state or in any situation, you know what to do, what move to do in this case. That's the schema allows you to categorize situations in the task domain and come up with solution moves for any of those states possible that the schema categorize. So for that, you have to attend to a problem state and learn what would be associated move for that problem state. That was regarded for schema acquisition, and that's exactly what example actually do. So in this case, learners in this case acquire doing these forward walking processes, not like backward, like in mean sense analysis. When they do the conventional problem solving, they use this problem search method, like mean sense analysis. And in mean sense analysis, they walking backwards from the goal with all these sub goals and all these manipulations with them, which is imposes heavy cognitive load, extraneous cognitive load. So what example essentially dealing with this extraneous cognitive load by replacing it with walking forward. They don't start from the goal. They start, this line is specific problem state, and this is a move for this problem state. Nothing else involved. So walking memory is not overloaded because you're dealing at a time with one state and the associated move for that state. That's what essentially walked example do. So again, it was since 1985 as it first was done this study in why walked examples are efficient. There was a lot of studies in absolutely different domains, in different areas. Also, there was some studies that frequently quoted by the Jew and Simon, and that the same Simon who was the Nobel Prize winner in economics on applying cognitive science to some economics problems. But he was involved in this instructional research as well. So they compare this like rebuild mathematics course instead of a lot of conventional this problem solving. They use more extensively walked examples mixed with problem solving as well. You cannot just do them itself, and that's allowed to reduce significantly the instructional time. But that was kind of large scale. So experiment, we don't do that in cognitive load. Cognitive load experiments usually are more kind of these controlled experimental, strictly controlled experimental conditions for some specific learning situation. So it's kind of more local type of experiment. But they compare and they find out that what example is really much more efficient than conventional problem solving. But they could be still not always applicable. There is some limitations of application. So firstly, what example are most effective for knowledge learners? So the learners, they don't have much relevant knowledge base in long-term memory, because if they have the relevant knowledge base, those worked example could become really redundant, because essentially they know many of those steps and associated moves that necessary. So if they know that, if they have the relative knowledge. So for learners who already have some sufficient experience in the task domain, some schemas, for example, maybe not effective, could be redundant, and effectively in some cases could actually inhibit learning rather than improve it, because experts in this case have to spend their cognitive resources on doing activities they're not necessary for them, but they still spend cognitive resources on those activities, like studying worked example unnecessarily. So they would better involve like problem solving to practice their already available schemas and automate them and so on. But instead they have to use their cognitive resources on study and all those redundant worked example. So that's sort of what come up with this so-called expertise reversal effect. That example of expertise reversal in this case, meaning that essentially for more knowledgeable learners, for experts, you can say in a domain, some of those techniques that are used for analysis would be actually inhibiting learning rather than improving it. So that's what the nature of that expertise reversal effect. But we're going to talk about expertise reversal effect in the next part of this series of lectures, which is our first topic, essentially. So we don't talk much about that today. So also worked example could not be efficient or effective even when they actually design in a way that impose some extraneous cognitive load, unnecessary cognitive load, meaning that some of those things that we discussed in the second lecture when we talked about working memory and cognitive, an introduction to cognitive load theory as a theory that looking how to get around this working memory limitation. And we look at some example like split attention effect, redundancy effect, modality, and some few others. So if worked example is designed in a way that actually violates some of those principles, so worked example design in a way that sources of information are split in time or in space. So the students have to split their attention between different parts of presentation, like looking for the diagrams and then reading text just in a different part of the page, and have to jump and between the picture and the explanation and keep in working memory meantime what was in that picture before reading the text and vice versa. So that imposed unnecessary extraneous cognitive load by itself. So it's not only would be worked example would be designed to reduce extraneous cognitive load, but in fact, if it's designed not properly, it could also impose some extraneous cognitive load or extraneous load of different kind of nature here, but would be still extraneous cognitive load. So therefore, they should be designed properly according to those techniques that are suggested to reduce those types of extraneous cognitive load. So all those techniques would be applied to worked example for them to be efficient. So of course, worked example, and I already mentioned with this kind of expertise reversal effect, but they are again most efficient for novice learners because they provide a lot of instructional guidance, all the necessary guidance included into worked examples. So, but when the learners become a little bit more knowledgeable, so if expertise, when expertise is increasing, then accordingly we have to reduce the level of guidance because they become redundant for them, those kind of detailed explanations. That usually suggested to be done gradually, as shown in this diagram. Eventually, when a level of expertise becomes sufficiently high, there's no point to provide any guidance at all. Only problems could be used just to practice and to automate some procedures. Problem solving could be used again with different degree, depending on that level of expertise. If everything automated, that no problem solving is finished. But normally with the problem solving to automate some schemas and to apply them in different practical situations and so on. But in some intermediate stages, some intermediate level of guidance need to be provided. Again, I'm not going to talking about this gradual transition in this lecture because we're going to talk about that in the following lecture in the following lectures in the part 2. But one of these obvious suggested means to do this gradual transition is using these so-called completion problems. That just simply like worked example, but with some steps replaced by just problem solving. So the students are presented partial worked example, some partial explanation of steps or partial steps provided, but some steps are not, a solution is not provided, but students are suggested to do it on their own. So meaning that, like in this case, the last step is replaced by a request to complete the solution, the students on their own. Number of those steps could be gradually increased, of course. In this case, completion problems could start from any of that stage. The rest could be completed on students should complete on their own, and so on. The series of these completion problems sometimes is called like the faded work examples, like another faded techniques, the faded principle of faded guidance effect in cognitive load theory. But again, that's something that we will discuss in more details in the following part of this series of lectures, so I'm not talking about that to detail now. So um, for now, what we're going to talk about for remaining part of this lecture is would be that sort of relations between explicit instruction and problem solving. In terms of worked example, it means essentially between worked example and problem solving, because it's not a trivial questions. Again, from cognitive law perspective, when we're dealing with novices, again, now we're going to talk about novices mostly. Let's forget about expertise reversal and expert, because for expert situation could be different, as we mentioned already. Worked example could be not necessary, explicit instruction not necessary, could be something like reduced guidance or even some unguided unguided instruction could be effective. We're talking about novices now. Still, for novices, cognitive law theory clearly suggests, based on worked example effect, that explicit instruction should always precede problem solving. So problem solving should follow worked example. So you provide worked example first, where students have acquire some at least initial schema in declarative form. Of course, in this case, it's not any procedure yet automated, but at least they know it. And then during the problem solving, the following problem solving, they just acquire that kind of procedural knowledge. The knowledge become procedural, automated, and so on. So example, problem, or general explicit instruction, then problem solving. But there is some other point of view that say maybe in some cases they say that presenting problems to explore first without for students who don't have any solution schema or any knowledge of solution procedure, giving them some problem first to explore and then give them explanations or guidance how to do it kind of properly. So it's another point of view. And so what the question is, what should go first, problem solving to explore or work example? Again, with cognitive law theory, with traditional, as described in cognitive law theory, the answer is unequivocally problems. Worked example or explicit instructions should go first, followed by problem solving. But as I said, some alternative views, for example, such approaches like productive failure, like preparation for future learning, invention learning, they argue that initial problem-solving activities, they are usually called generation phase of that kind of instruction or exploration phase. Preceding explicit instruction could be efficient for teaching novice learners, actually. We're talking about novice learners. So here's some research and some researchers who represent those alternatives use. It's a lot of empirical evidence was accumulated in those areas, and so it should be regarded seriously, because there is a kind of, apparently there is some contradiction here, because it's everything, again, for novice learners, attempts to theoretical reconciliation here. Of course, some weak attempts could be done referring to expertise reversal effect, but it's not really quite explained, because, yeah, we can say for expert that problem solving is fine, but they're talking still about novices. So it's all about novices. So expertise reversal, it actually explains when problem solving based instruction could be appropriate for more knowledgeable learners, the answer is, but those alternatives you're actually talking about still novice learners. So it's not about more. So that maybe not quite an explanation. Another explanations was based on considering element interactivity. So for which is argued that for low element interactivity, problem solving type of generation type of instruction could be efficient in actually in agreement with this kind of productive failure and other approaches. But for more high element interactivity material, more complex materials, element interactivity we discussed when we talked about lecture 2 about working memory load, that load is caused by essentially the degree of element interactivity. If there's not much interactivity, element could be learned each one at a time, there's no problem. But if you have complex materials, then cognitive load is high. So the argument here was that for complex materials, high element interactivity materials, explicit instructions should go first, but for low element interactivity materials, problem solving or generation could be, in this case, activity could be appropriate as well. Again, it gives some explanation in some specific cases, but generally still not quite, because that evidence that obtained in those alternative point of view, actually, they use complex materials with knowledge learners. So, and they say that we've got some empirical evidence that problem first approach is working well. And also some types of knowledge were considered as well. Some maybe worked examples are good first for procedural, but when we learn in conceptual, maybe in this case, vice versa, those type of approaches could be effective. There was some evidence here. It's not really evidence really, but there were some ideas in the first study. There was some limited evidence. It is some possible point in this view, but there's not much empirical evidence still accumulated in this area. So that kind of gradually something that I consider that maybe better explains situation and this better means of reconciliation than other previous kind of attempts here. And then finally, that what suggested, and what I'm going to talk more about, these kind of suggestions that consider specific instructional goals. There's that sort of idea to try to reconcile those kind of point of view, alternative point of view. And the important point is that those alternative point of view, they don't deny the importance of explicit instruction. That's not that they say it's not about discovery learning or inquiry learning. They don't say that just present problem to explore and nothing else. They're talking about explicit instruction. But they say that explicit instruction should be preceded by exploratory problem solving. So they not deny the role of explicit instruction and worked examples. They just say that explicit instruction should be preceded by exploratory problem solving. So they don't deny either explicit instruction, neither the problem solving after explicit instruction as a means of practicing and automating. That also not deny that was shown that necessary and efficient kind of part of instruction. But what they say is that exploratory learning first should be efficient. We tried few experimental studies to compare those different kind of different type of approaches, problem first or explicit instruction first. There is two type experimental design. In this case, if you want to experimentally compare those two different approaches. First is just reversing the sequence. So comparing example problem with problem example. So you just reverse the sequence and that's it, nothing else. The good point about this experimental design is that essentially everything is the same except the sequence. So from experimental design point of view, the argument will here be that okay, that's a real actually comparison because we have all the other factors equal except the sequence, and therefore we which sequence is more efficient. So again, traditional cognitive load approach here argues that example problem should be significantly better than problem examples. And again, that result was shown in many studies. Okay, there is a little bit problem with this experimental design because those alternatives point of view that argue for the value of problem solving, then actually again they not, as I said, they don't deny the role of examples, that they just trying to say what should precede the example. So there is some alternative type of experimental design that I personally believe is more relevant for testing this sort of idea, what should precede explicit instruction. And in this case, we need to keep all this explicit instruction phase in the form of example, in this case, the same in all types of conditions that we compare. For example, we should compare unguided problem followed by example. We should include some maybe partially guided problem, again followed by example. Finally, we could compare when the first phase actually is also explicit instruction and followed by another explicit instruction again. So the point is that second phase is kept constant and fixed according to what those other alternatives kind of view say. They all say they say that explicit instruction is necessary, but it should be preceded by what? Problems, they say, okay, we will test this in the first type of experimental condition here. Maybe they should be preceded in another explicit instruction. Example. That would more like test in this case more like a cognitive load type of argument. If what example is so good, that example should be of course better than unguided problem example, right, from cognitive load point of view. And some intermediate stage could be included here, intermediate condition with some partially guided problems, and see maybe that would be something that's relevant. So again, a lot of studies were performed in this reversing the sequence, and a few studies was performed with this type of design with the second phase fixed. I show you few of those examples, few of those studies that I was participating myself and what they actually shown, and how they actually generated this idea about the importance of goal as determinant of optimal instructional method. So in this study with one of PhD students, it was done in physics with novice learners, of course, because we're dealing with novices only. Again, 4 conditions were compared. So again, according to this second type of design, second phase was always the same, explicit instruction. But the first learning phase was different in different experimental conditions. So again, in one condition was just problem. In another condition was the problem solving with some partial guidance in principles used for solving this type of problem, physics principles. Third condition in first phase was problem solving again with principle, but also with some reflection, metacognitive reflection on what happened during that sort of application of those principles and so on. And finally, the last one was just explicit instruction, full explicit instruction with principle guidance, maximum guidance, and all of those 4 variants of first phase were followed by the same fixed explicit instruction in the first phase, in the second phase. It was just principle-based work examples. Just quickly to run through to show you some sample of those experimental materials. This was this type of problems, just collision of object in physics, pretty complex in a senior high school physics course. So they're using the conservation of energy and conservation of momentum principles. So here they presented some example of those principles. Initially, principle 1, principle 2, the principles are described, and here is a worked example on the right-hand side. So as you see, pretty detailed instruction with both with principles and examples provided. This is kind of this version with worked example. One with problem solving. The one which is a problem solving with principle guidance was the same principle described, but instead of worked example was just the task, solve the problems based on those principles. So there was some partial guidance. And of course, the problem solving only was just problem statement, like was shown initially, without any principle guidance and anything else. So, yeah, so that example of principle. In the second phase, it was just use explicit instruction in the form of worked examples with principles, as in this case. Again, some of those details. I'm not expecting you're going to read all the details, just showing you how that look in general, just skipping through this. So quite serious worked examples in that rather complex topic with a lot of guidance in form of those principal worked examples and all these detailed solution steps and then those 4 experimental conditions. So what the results showed, actually, very strictly controlled some experiment with everything else is the same, except those different experimental, different type of instructional approaches in the first phase, which follow by the same second phase. So the results show not really evidence for the problem solving. First was better than full explicit instruction. No significant difference, no evidence of in favor of those productive failure and other problem first. So, but on the other side, also no worked example was obtained, because the worked example condition, meaning that full explicit condition number 4, which was explicit followed by again explicit. That no worked example is that worked example condition didn't outperform other conditions in the test. Both immediate and delayed some type of post test were used. Immediate, so right after instruction, delayed sometime like week after the instruction. So we don't have significant difference in favor of either this or other approach. The thing that some significant difference, they show only that initial problem solving with principal guidance and reflection activity was significantly better to when the was problem solving first was used without principal guidance and reflection. So it appeared to be that when using problem solving initially, exploratory problem solving. So it's better to, from this result, meaning it's better to supplement it with some principal guidance and also give students some time to reflect on what they did, some metacognitive kind of reflection here on what they done and how those principles could potentially be applied. So also from point of view of cognitive load, learners in this problem solving only condition without any guidance or reflection invested most actually cognitive effort in the first stage relative to all other 3 conditions. So, and again, it's kind of expectedly because those students were dealing essentially with this problem-based search only, and as we know, they are pretty much cognitively taxing. So they invested a lot of cognitive load. But the main result here, there was some partially interesting kind of result in relation to what of those problem solving could be better, but eventually no difference between the conditions. Another study, which is a pretty much similar and a similar result in mathematics area. So in this case, again, not 4 but 3 level of guidance was some unguided attempts at generated problem solutions, again followed by explicit instruction, partially guided attempts followed by explicit instruction, and a comprehensive full worked example guidance, again followed by explicit instruction, the same for all 3 conditions. The task that I used here was some geometry task of this type, just using those instruments, the compasses and ruler. I guess you have to divide this kind of in half, and this is an example of a task with some partial guidance. This middle part showing some what the ancient Greeks used, and that kind of use as a sort of partial guidance, some hints to students to give them some hints, some partial guidance how to solve these problems in general from below. So again, I don't give more example, but this kind of type of task and this kind of type of partial guidance and full guidance actually represented step by step what you need to do to do this kind of task. Again, similar result, no differences between 3 conditions. Again, there was some differences in cognitive load. Worked example reduce actually cognitive load, again, expectedly. And there was some motivational scale used in this study in difference from the previous one. And they showed that on some motivational scale, some conditions were more favored than others. So, for example, on interest and probability of success, that worked example condition, which was fully explicit instruction, was the best. But on challenge, some unguided problem solving was better. Kind of showed a better motivation in this case, motivational scale. Again, some partial result, but most importantly, no differences. So, what's the result? What the conclusion from those studies? Other than were actually the only studies that I was participated in publications that were published, even though there no significant differences were obtained. It's not that easy to publish if no significant differences. For me, these are really the only 2 studies that I ever published with no significant differences. And the journals was quite serious. It's not just some instructional science in one case, and I forgot what I want to do, but that's some. It was kind of highly rated journal. So it was a lot of reviews on that, and a lot of critical comments that we have to respond. And eventually, after several stages of review, and actually they were accepted. Because of course the reviewers also indicated the same. There's no significant difference. But the theoretical background that we actually use here to argue for the usefulness of those non-significant differences essentially was based on this theoretical framework that I want to talk about now, that actually the instructional goals in those different phases could be different. So especially in those different phases in those approaches, alternative approaches, have different kind of instructional goals. When you're talking about initial exploration in productive failure approach, they never talk about students learning anything in the first phase when they suggest, let's explore this problem first before I give you some explanation. They don't expect that students will learn solution procedure for this attempt. There is some different goals of that. In the second phase, when explicit instruction is presented, even in this productive failure approach, the goal is, yeah, that they have to learn the solution procedures, the schema, if you like. But in the first phase, the goal is different. And if the goal is different, the question is, would be relevant actually or valid to compare in this way those two phases, like in this approach when you just reverse the sequence. Because when you reverse the sequence, you assume that goals are pretty much the same. When in fact, those people assume the different goals for different phases. Therefore, the goals should be taken as into consideration. And this study essentially is no significant difference between those approaches, actually showing that those different approaches that realize a different sequence of instructional goals and look like those sequences, both of those sequences could be valid and work. So you can define sequence of instructional goals in different ways. And some of those sequences could have the same instructional effect like possibly other sequences. It's no sequence of goals that you can predeterminedly say that this is definitely better. Maybe in some cases, yeah, but we have to explore and find out which sequence of goals could be better. But effectively, our explanations for those non-significant differences was that those studies essentially realized different sequences of instructional goals, achieving sort of different, realizing those different goals and different phases of instruction. So, getting back to this theory versus empirical evidence argument, so how we can get into again to this question: is it possible to reconcile this result with cognitive load theory, those productive failure, invention learning, and other things, with a problem first? Oh, sorry, I go back. So, do we need to revise some basic approaches of cognitive load theory, or should we define some boundaries of cognitive load theory, whether it's applicable in some cases and maybe not exactly in other cases? So we need to look kind of critically on this where cognitive load theory actually is applicable. Any theory, if it's theory, have some limits of applicability. If it doesn't have any limits of applicability, it's not a theory. It's kind of sort of a religion or anything of this kind of dogma, but it's not a theory. Any scientific theory, and my training as a physicist, original, it just deeply embedded it into me. I was trained in theoretical physics, that there is no theory without boundaries. You take any theory, Newtonian, relativity theory, quantum mechanics, anything, all those theories have some boundaries. The same in any serious theory in psychology and so on. What are the boundaries of cognitive load theory in this case? There should be some. We have to explore. That's what was involved for some years into this. And so, again, I'm getting to this. I like to use these examples from simple linear algebra equation, just to get some initial ideas. If we have this simple task, and I use this task many times for illustrating different things, to solve this equation for x. Okay, we can teach students to do this most quickly probably, and from this point of view most efficiently if you want just to learn them, to teach them, just in this way, just presenting them worked example and showing them how to do that, like this. And yeah, that would be probably will take least time, and they quickly would know and remember this kind of procedure. From this point of view, would some activity like this would have some value or not? Just that trial and error that I showed you in the last lecture as an example of some trial and error, which is presumably inefficient instructional technique, as I argued last lecture. But would that activity could be valid or useful in some cases or not? For teaching the solution schema, not, because that was I argued last time. Impose a lot of working memory load, and students wouldn't come up with a solution schema after doing many of those activities. In some study, in some practical case that I taken this example from, it was 20 tasks like this. Student did all 20 correctly, come up with correct solution, and no idea about actually a simple solution rule divides this right-hand side by the coefficient. It's simple as that. No, there was so as a for the goal of learning solution schema, this is not good. But what would be the other goal? What the other goal would be just some getting into some understanding the nature of these tasks. Could that be useful or not? If they do this kind of activity, they have some possibly idea how those parameters relate to each other. You know, because they substitute x with some, do this substitution with different values, and they see what's happening. Some cases it getting closer to that -4, sometimes get it further. So they get in some understanding of what the nature of the problem here. So it's not completely useless activity from this. So if you are very limited in time and a time pressure, and if you need to teach your students just solution procedure quickly, so they can use it, then worked example on that left-hand side, the best way. Because the goal is teach the solution procedure. If you have sufficient time to give the students exploration, so you can expect that maybe they have some kind of better understanding of the nature of the task here by getting involved in some of those presumably useless but still activity. From my personal experience, when I was studying physics, I remember I was doing some of those useless activities in many for some tasks, but for hours, which is very completely useless. You can read the textbook and see how the correct solution is, and learn it and apply it. But you do some of this kind of calculation with specific numbers, building some diagrams for specific numbers, and that give you some kind of understanding of the nature of the task better when you get involved in these kind of things. So that kind of idea was that it's not completely useless possibly, but the goal of that activity would be completely different. It could be something that understanding of the nature of the task or something like that. You know, to getting some prior experience in this kind of task and getting familiarize yourself with some kind of nature of the task or anything else. But some kind of goals, but definitely different from the goal of just teaching solution schema. So based on this kind of consideration, again, we come up with this sort of understanding that maybe we have to look at a cognitive load theory from point of view of that kind of what the goals is achieved and what the instructional goals is actually is in front, and for which instructional goals this cognitive theory is the best, and for which instructional goal maybe not the best. In order to give some kind of theoretical substantiation to this point of view with those instructional goals, we have to again look critically on a level of analysis in cognitive load theory, because when people talk about cognitive load theory, they talk about cognitive load you can find in literature different views. Some people talk about cognitive load when the students do specific simple operation in these moments of time. Other people talk about cognitive load when the people learn the whole topic. Sometimes you can even say they're talking about the whole course. So the scales are very different. So we need to set up what the correct actually is this unit of analysis in this case when you're talking a cognitive load theory. So from this point of view, again, kind of redefine a little bit the cognitive load as the intensity of cognitive processes within the time scale of working memory operation. So cognitive load is about working memory limitations. Working memory operate on a time scale of seconds or maximum minutes, if you like, that something like in this scale. It's not about hours. It's not about days. It's more about seconds or few minutes or something like that. That's what working memory operation scale that we discussed when we talk about working memory. Duration of working memory, what was limitations? Like up to some studies show up to 18 seconds. So it's just less than a minute. So that time scale of working memory operation. And when it talks about that working memory is overloaded, it means that it's overloaded on this time scale during those seconds or on the minutes, something like that. We're not talking about the hours or days and so on. So, and what happening with this within those seconds or on the minutes or something like that? A lot of processes, some manipulation, some processing information, activation, some prior knowledge of things, bringing some prior knowledge, activating from long-term memory, a lot of things. And describes those lot of things, cognitive load theory trying to describe it as in terms of element and interactivity. That's good approach because it's pretty much something that we can operationalize in specific materials, but it's not kind of complete. It's idealization. In reality, a lot more happening there, not just some isolated elements interact with each other. Happening a lot of cognitive processes there that is difficult to quantify and difficult to describe and even describe in terms of elements, because what's happening there, that all these cognitive processes, and that could be a different kind of intensity, could be a lot of those processes, could be less. So we can say that some intensive cognitive processes happening within limited amount of time, and a great number of that would be definitely working memory would be overloaded. Element interactivity essentially give us one version of this, a lot of interactive element with this limited scale of time and capacity, and that produce cognitive load. In more general case, I would say intensity of cognitive roles processes within working memory is high, and that will generate cognitive load theory in more kind of general. It's kind of more general approach in order to come up with this level of analysis. So from this point of view, the cognitive load phenomena is something of that local level. It's a micro level actually of processes. It's not a macro level, it's micro level. It's something that's happening with those time scale of working memory operation. Seconds, or let's say minutes just in case, but it's usually even under minute. So just kind of local micro level processes. When we're talking about the greater time scale, it's actually accumulation of those local micro level characteristics. It's a kind of cumulative nature of this cognitive load on a larger time scale. So something that was experienced overload in the earlier time could affect the processes later in this cumulative way. Because if you have heavy working memory load locally in some previous kind of moment, the later that would affect, of course, because you were overloaded, you missed something probably because of that, and that definitely would influence what you learn and how you learn a few seconds or minutes later. So in this cumulative nature, cognitive load operate on macro level, on a larger scales. But by itself, cognitive load as such, a working memory on site, is a kind of local micro level characteristic of cognitive processes, and that's how we can regard it. So in this case, we need that micro rather than macro management. We need to manage on micro level what's happening at this moment and this time with this kind of specific learning tasks they are doing right now, or operation that they're doing for performing some specific goal. From this point of view, what is important, what kind of goal you're trying to achieve in this type of specific activities that you're doing in this micro level time. So that's where this idea of goal could be kind of substantiated, because the goals would be related to what you are doing at this specific current moment on micro scale, on that kind of time scale. So considering generally specific goal of different activities, the cognitive load theory traditionally consider only one type of goal: acquisition of domain-specific schemas. You wouldn't find any other description of any other goal in cognitive load theory. You read any kind of paper, any text, and you see that it's about acquisition of domain-specific schemas. That's the only goal stated. So, from this point of view, we can say that we can have some kind of sort of contradiction, if you like. So, this is pretty much goals are stated as a macro level for the whole goal of instruction, acquisition of schemas. But on the other side, we have this macro level of cognitive load phenomena with the different activities in different specific local kind of times, local micro level. So resolution of that would be considering specific instructional goals of those cognitive activities on micro levels. They need to be considered in the theory, become kind of the attribute of the theory. So what specific instructional goal on micro level, when you're doing specific levels of a specific task on this micro level of cognition, what is goal of that activity? Is it acquisition of schema or is it something else? So it could be acquisition of schema. In this case, the cognitive load theory to be applied. It could be something else, something that, for example, I would call in some papers kind of lower level pre-instruction goal. Instruction goal would be acquisition of schema. Pre-instruction goals, that's something that forms some prerequisite of learning schema. For example, I guess I provided some example later. That could be some motivation, explorations. Exploration is a means. Motivation, activation, prior knowledge, or many other things. In those generation, exploration phase of those alternative points of view, like problem solving first approaches, they actually consider some type of those goals for their generation exploration phase. So they consider, for example, activating prior knowledge. They consider some exploring initial ideas related to some conceptual features. They consider enhancing awareness of the problem situation, like some of those trial and error attempts would be something like that for enhancing awareness of the problem situation. Something like this. This is kind of pre-instructional type of goals, not acquisition of domain-specific schema as such. So some of those generation exploration phase in alternative approaches actually, presumably, as they declare, they're working on achieving some of those goals, not acquisition of domain-specific schema. And that's something that would be kind of pre-instructional goal in some of those local level of performance, of local level, of micro level of analysis. So from this point of view, if we're talking about achieving some of those alternative goals, so high level of cognitive load might not be something that would interfere. So when students do these trial and error attempts in order to enhance their awareness of kind of problem situation or something like this, or problem task, they can experience high cognitive load, but that cognitive load would interfere because they don't learn in a schema, domain-specific schema here. Cognitive load definitely would interfere with that. We know that. Mean sense analysis, trial and error, they impose heavy cognitive load. Last lecture, we discussed this. And that because of that, the problem solving in this case would be inefficient. What examples should be used? Cognitive load argue for that. For learning domain-specific schemas, but for achieving some other goals, maybe not. Maybe high cognitive load not an issue, so therefore that kind of the boundaries that we actually in this case facing. So that might be, they would contradict cognitive load theory because their goals are different. So implication of that kind of consideration or suggestion is that for some goals, other than acquisition of domain-specific skills, so immediate sort of that direct instruction might not be the best possible optimal way of achieving those goals. Some of those problem exploration would be more suitable for achieving those instructional goals, not the schema acquisition. So from that point of view, the learners may do some of those activities that are absolutely no from cognitive load point of view, because they impose heavy cognitive load and interfere with schema acquisition, but they don't interfere with achieving other goals. So therefore, they're not violating actually cognitive load theory principles, because cognitive load theory principles applies to schema acquisition. So all those type of activity like initial discussion in problem-based learning, that exploration in productive failure and so on, that was in those alternative point of view, they essentially they directed to different goals, and cognitive load which present of course there, and high level of cognitive load might not really be extraneous, because they are not extraneous for those goals that are achieved in those activities. So again, this kind of defines some possible sort of boundaries here, then we need to look. So whether to use, in this case, direct instruction, minimal guidance, or partial guidance in complex problem solving, which in complex problem solving, I mean the problems that involve different sort of type of activities and different stages. Depends on specific local instructional goals on those specific local stages. So therefore, those complex learning environments should use those methods that are optimal for achieving specific instructional goals, which should be achieved in those specific type of activities, in those specific phases of the instruction. The complex, like problem-based learning, for example, normally it's very complex learning environment, which includes a lot of different activities throughout, and those different type of activities usually have different types of goals. Not all of them directly targeted schema acquisition. Therefore, if some of those activities are used there that not optimal from cognitive load perspective, they might be not an issue and not a problem, because the goal is not of those specific activities, not acquisition of domain-specific schema, but something else, some of those pre-instructional goals also, or motivating and so on. So therefore, or effective motivation and different aspect of learning. So, therefore, I think that this dilemma that present in instructional science, that people argue a lot, what is better, this instruction or problem solving, and everybody uses their own argument, and they talking past each other, and they talking essentially different things, because there is this dilemma. Again, it's not really a dilemma, because you have to consider what you want to achieve, and then select appropriate instructional means for that. So therefore, I was arguing for some time for moving away from this kind of dilemma when you're talking about complex learning. That's kind of learning that on micro scale, that include many type of learning activities, because in this case, some of those activities could have different instruction. But if you have just one simple task, the simple activity with schema acquisition as a single goal, that the cognitive loads are only things to do. But if you put other, you have to balance, and you have to consider others. So Again, I just repeating this, that with different variety of activities involved with kind of those complex instructional method, um, that contrasting this explicit instruction and with a limited guidance instruction and problem solving would be meaningful only on that local level, depending on that goal of that local level, not overall for the whole complex learning task. On local level, you can argue if it's schema to be learned here, that cognitive load approach is the best. If it's some other goal, some of those pre-instructional goals, as I call them, some another approach could be possibly used, then followed by another activity, which is based on cognitive load for schema acquisition. Essentially, schema acquisition is a really macro goal, is an important goal, is the most important goal of any instruction. We learn things that to acquire some domain-specific schemas, but on the way to that learning, it's a lot of other things need to happen. Some of those pre-instruction goals should be achieved, and therefore some of those activities and approaches could be relevant. So that's my kind of view on this on these things that I wanted to discuss. And finally, just a few words about this evolutionary perspective that we on the lecture one, I suggested that maybe when we're talking about acquisition of secondary knowledge, we're not motivated to acquire secondary knowledge. We're internally motivated in kind of to acquire biologically primary knowledge because that's something that we're predisposed to acquire rapidly, just being involved in different activities, but we're not predisposed to be motivated to learning like scientific knowledge, anything. We need to be motivated. And therefore, for acquisition of secondary knowledge, we need to be motivated. And that not really covered in a way by those principles of evolutionary principles that tradition would describe 5 principles, because they're pretty much the same for any system, for biological system, which operate mostly on this intuitive type of knowledge or equivalent for other biological system, primary knowledge, and the same for human cognition. Therefore, I suggested that firstly we need to consider the human cognition and maybe some equivalent levels of cognition or cognitive system, like more higher level. I call them kind of provisionally kind of intelligent natural information processing system, and they need to be characterized by additional principles. And I suggested some principles that intention to act or preparedness for learning principle based on some other studies, and intention. Eventually, I come up with that would be called like intention to learn principle. Intention to learn meaning the intention to get involved, engaged into acquisition of that secondary knowledge, which is presumed motivation to do that. And that would cover that type of activities and approaches. Therefore, because this principle in a way would unite, if you like, this acquisition of secondary knowledge, cognitive part, and motivational part of that engagement to acquire this intent to acquire that type of secondary knowledge, that kind of motivational part. In this case, we have this pretty much, we see how these motivational and cognitive parts are interrelated. They pretty much, cognition and motivation fundamentally interconnected, because there couldn't be learning of secondary knowledge without presence of this intention to learn, meaning that intention to get into that learning secondary knowledge, which presume motivation and engagement in this case. So with this, if that principle added to those 5 available already for intelligent level or intelligent natural information processing system, that would organically integrate and interconnect on that fundamental level with cognition and motivation for this type of intelligent natural information processing system. And that would actually, as one of the kind of implication, would require that importance of designing some learning activities that have those pre-instruction goal like motivating engagement or some other relevant goal. So in this case, on this fundamental level, we can say that some of those activities would be necessary, and some of those activities would be required to be designed. And when we apply these principles to human cognition and to learning, so that's kind of this sort of big picture view on this kind of a relations of that explicit interaction and unguided problem solving and their role and so on, and those instructional goals. On this fundamental level of kind of evolutionary principles, it still can be kind of explained on some type of principle on that high level. So possibly, that's just again some theoretical suggestions that I'm proposing in this case, and I believe that that would be something that would give us better understanding of the field and the role of those human cognitive attention characteristics, and also the place of cognitive load theory, the boundaries, limitations, applicability, and so on. In this case, we can talk about this in more specific sort of level. So that's what I wanted to talk about. For the next part, which I plan to do during my second visit in 2024, which is planned, this visiting Leverhulme Trust visiting professorship was they allowed to divide it into two parts. So one is happening now, and one part would be the second part in 2024. And so 5 lectures in this part and 5 lectures presumably was identified for the next part in this case. So the next part, just briefly to say what I'm planning, the one would be, the logic is pretty clear now because it's based on what I'm actually, the topic that most close to my actual field of activities in this cognitive load theory, expertise reversal effect. That's my area. Prior knowledge principles. That would be lecture on this. Managing instructional guidance based on this expertise reversal effect. These fading techniques and other things. That would be second one. Rapid diagnostic assessment. How to assess level of expertise. We cannot do anything when we talk about expertise reversal and how to use instruction with more novices or more experts without actually diagnosing what their expertise level is. And diagnosing sometimes rapidly. There would be specific lecture about this rapid diagnostic assessment technique that was developed specifically for these purposes, which is pretty useful in its own terms also. Then another one, organically from other 3 coming out, would be tailoring instruction to level of expertise, or adaptive instruction based on this rapid assessment as a tool. Coincidentally, the project that we do with how here during this visiting scheme is a project actually designing some adaptive instruction for primary school mathematics based on rapid assessment. So essentially, all those topics will be more directly related to these projects that we actually do. In parallel with these lectures, what I involved in the projects, we develop now experimental materials to test some of those and so on. So possibly I can use some materials already even from that specific project next time, and even possibly we will get some result. We can show some possible result out of that. So those 4 topics are pretty clear and very clear. The iron kind of logic here, which is all 4 lectures. The last one I just indicated as the future trends, meaning that I don't know what I'm going to talk about yet. If I don't know, we say about future trends, but that will definitely come up. Maybe it would be some future trends in this case, so it would make sense. But in this stage, it's too early to clearly indicate exact specific topic. But future trends seems relevant as well. So that would be plan for part 2, and that's all. So thank you very much for your attention.
So any questions?
Can I just say how pleased I am to hear what you were saying, because from a teacher's perspective, what we're seeing in school is over-application of worked examples for absolutely everything, and we're just seeing all the joy being taken out of maths teaching and all that exploration. And because teachers are seeing this, we've got to do it this way, we've got to do I do, we do, you do. And I'm really pleased to hear you say that that's not the only way to teach, because I knew that, and I was sort of saying it's about the way people are applying cognitive learning, they're applying it a blanket across instruction, whereas it's very much about procedure. And I think that I'm really pleased to hear you say that there is a reconciliation between that problem-based learning and the cognitive load, and there isn't. I was trying to work out what the conflict was, and I think you put it, I'm really pleased to hear you put that.
Let me just comment a little bit on this, because I don't want to be like a provocateur here, just within a cognitive load theory. I am still in cognitive load theory.
No, I'm not saying.
And cognitive load theory argue for worked examples,
Yeah.
but we need to see where they are most
That's
efficient
exactly
and
what
use it there.
Yeah, that's what I want, and I'm saying to people, it's not applicable in every situation, and that's what I'm really pleased to hear, that you're going to do some research and where it is applicable, where it's not. Because for me, I'm seeing it's applicable when you're teaching procedures, but it's not necessarily applicable in teaching, particularly in motivated children, but also in teaching inquiry and curiosity and promoting all of those skills that you want children to have that are not just following procedures. So I think
The procedures are important,
absolutely,
and they should be,
important,
and they should be instructed, of course, by best thing, but we argue cognitive load theory as working examples.
Yeah, and I'm saying that.
But some other goals that we have
Exactly,
here.
I think that's it. I think people are forgetting there are other goals and thinking that this is the way to solve all problems.
Well, but can I just add, just following up on what you said, I am really glad to hear what you said, but for the opposite reason. Because in Canada, procedures are out the window, right? Like it is a bad thing to use procedures, at least in the province of Quebec. And teachers are explicitly told, do not teach maths, do not teach procedures. They must be doing only exploration, only this creativity. So I'm glad to hear the reverse.
Yes, I think it's finding that under the ground.
Yeah.
It's all there. It only needs to be done, doesn't
And it depends on
it?
your
Goals.
That's what I try to say to teachers in my professional development. And they're relieved to go, oh, I can actually do procedures. Yes, you can, and you should. But it depends on what you want to teach, right?
Yeah.
So this research is extremely important for these reasons.
So, yeah, I'm trying to argue about this kind of balance approach that everything, because look, there is a lot of empirical evidence in cognitive load theory, and we regard it seriously, but there is a lot of evidence in other areas as well, and we need to look at it seriously. We're not just dismiss it completely. There is some result in these productive failures. They published it for 20 years already, and they gotten some results. Okay, we can criticize some of them sometimes that not design is not properly done on some experimental procedure. There was some mistake, but some look like they are pretty legible, and it's getting some result, and we need to take them seriously. We just need to dismiss. And taking it seriously, meaning to define where those results apply and where those results may not apply. So we need to have clear boundaries, clear criteria where the specific theories are applicable, and then use them in balanced way. In this case, for achieving specific goals for which those theories and those approaches are best suited.
Thanks, Slava, very much. I just want to second what Helena was saying. She's from Canada, I'm from New Zealand. We have exactly the same problem in New Zealand, that work examples is basically taboo. Children are expected to work it out, maths, quite this learning is. It's been around for 15, 20 years now, and our result estimation has just Yeah, it's just threefold, yes. And when you talk about balancing these approaches, I think the danger is because there's a lot of momentum has been generated by John Sweller and others who's bringing this cognitive loop theory. And I'm a bit concerned when you're saying let's find balance, it kind of that message might not be taken seriously anymore. And I urge you to approach it with caution because when people talk about balancing, from my experience, they're still saying I do, you do, I do, you do, you do. It's not the approach to take and the inquiry. So basically, they're arguing against providing any explicit explanations by an expert, saying the role of the teacher is to facilitate learning. And so when this balancing is brought into the question, it's not really actually about balancing. It's same old inquiry-based learning, just with a little bit of, I don't know what, but they will find a way. They will find a way to misrepresent your message. So
This is the magic bullet. This is how we have to do everything, and it's not that balance is not being considered. That's really interesting to hear.
In this second half of this lecture, I could have appeared like some arguing against the cognitive theory, but it's not the case because I just arguing for applying it to the best possible way to achieving the best result. Yeah. And taking into account some additional other situations, other things could be optimal as well. So, thank you very much for the encouragement.
I was just going to just pull up on that comment. The notion of balance, I think practitioners think that balance is you have to do a little bit of this. And I think your message is very different, right? It's about intentionality. What approaches are best for the goals that I want to achieve, which is unfortunately something that practitioners don't think a lot about, the conditions under which approach is appropriate. Right? So I think, in terms of encouraging you moving forward, if you are going to be, working with any kind of educators, I think that distinction is really important to make. Because if you use the word balance, you're going to go, I just use a little bit of everything. And then you'll be fine. And then, of course, a good approach. Yeah, exactly. And then it could also be, well, if I use a little bit of everything, you can use more of this thing that's the kind of the current flavor of the month, right? In my community. So I think that your message is really, really important. And just to let you know that it's that word balance is often messaging.
Yes, I think it's intention. The intention is the goal. The intention isn't it? That's the key thing. What do I want to achieve on this?
Yes.
Exactly.
Thank you.
Thank you.
Is any question online? Any question online? You can check.
No, thanks everyone.
Okay, thank you.
So when are you coming next year?